the rise of a single sphere along the axis of a rapidly rotating container. Okay, so here is a sketch of the configuration, and on the right you can see a sketch of the original device that was used by J.I. Taylor in his famous experiment in 1923. And so this problem actually, although it's very simple, has a broad range of applications. For instance, in chemical engineering, since we are in a chemical engineering department. In chemical engineering, of course, it's relevant with respect to separation techniques using centrifugation. From a more fundamental point of view, it's also relevant if you want to get some more insight into the dynamics of rapidly rotating suspensions. But actually, in the 1960s, well, the main motivation to look at this problem was related to MHD, because there is, as you know, there is a close analogy between a conducting fluid in the presence of a vertical magnetic field and a rotating fluid. And for this reason, there was the idea of using a rotating fluid in order to get insight into the motion of the electric particles in a conducting fluid. Also, this is a problem which is very relevant in geophysical fluid dynamics, especially with respect to the dynamics of liquid cores in the formation of terrestrial planets, although, of course, rotation in that case is usually combined with compositional convection. Anyway, so this problem actually is governed by simply two non-dimensional parameters, one of which is the Rossby number, which is basically a measure of advection effect compared to rotation effects, and the Taylor number, which is defined here, which is just a Reynolds number based on the rotation rate. And by the way, this Taylor number is just the inverse of the Ekman number. And of course, you can eliminate rotation in between these two in order to form a Reynolds number. Okay? And as presumably most of you know, in the limit of very low Rossby number and very large Taylor number, actually the vorticity balance reduces to this very simple form, which is known as the Taylor-Proudman theorem. And this simple form tells us that this dot product has to be zero in this limit, and this dot product being zero means that actually the velocity field should remain invariant along the direction of rotation, which also means that if it's not invariant, it means that there are either finite Rossby number effects or finite Taylor number effects, especially in the boundary layers, or there are blocking effects which are introduced by the presence of walls somewhere in the system. And also this Taylor-Proudman theorem has a very well-known consequence, which is the formation of Taylor columns, which are at rest with respect to obstacle, and I will show one of these in a minute. By the way, an important historical note, which is that J.I. Taylor and Joseph Proudman apparently never worked together, but they died one day apart from each other. Okay, okay, so let's jump to the experiment that was carried out by Tony Maxworthy in 1970. Actually, Tony carried out a series of experiments in various devices, but the one I'm going to talk about is let's say, the major one he carried out in he published in 1970. So here is the device. Basically, that was a tall cylinder, 1.5 meter high, rotating at 2 rounds per second. And that was, for that time, that was already a major experiment. So centimeter-sized spheres were introduced at the bottom, and they were released along the rotation axis. And Tony drew 2 horizontal lines around, let's say, the medium part of the cylinder. And just by using a stopwatch, he measures the time of flight of the sphere in between the 2 lines. And from this, he deduces the drag. Okay? And so here is a view also of what he got in terms of formation of the Taylor column, because he introduced dye at the bottom of the cylinder, and you see the sphere rising up along the axis and then training with it this long column of fluid. You see? So this is directly a manifestation of the Taylor-Proudman theorem, although the Rossby number is not 0 in that case, but it's already small. Okay, but this is the major result Tony obtained actually in this experiment. So what you see here is the drag coefficient plotted versus the inverse of the Rossby number. And you see that on the right half of the graph, there is a very nice, let's say, agreement between the drag coefficient agreeing with the theoretical law derived by Stewart in the implicit limit 2 decades before, and this theoretical law tells us that, in principle, for low Rossby numbers, the drag coefficient should go at the inverse of the Rossby number. So there is a very nice agreement, except that there is a significant offset by 70%, 70. So here is the theoretical prefactor that was derived by Stewardson, but for some reason, in the experiment, Maxworthy found a prefactor which is 70% higher. And this has been puzzling people for more than 50 years. And this was our main motivation to revisit this problem on a computer, try to understand where this offset comes from. Okay, so we wanted to reproduce this experiment on a computer, and of course, take this opportunity also to explore the characteristics of the flow field, which Tony couldn't do because he didn't have PIV at the time, of course. So the numerical setup we use is very simple. So we solve Navier-Stokes equation in the rotating frame. We hold the sphere fixed at the middle of the domain, so there is no differential rotation between the sphere and fluid, although we also used for some computations a torque-free condition, and we were able to show that there is almost no difference regarding the drag, at least in the limit of low Rossby number. Okay, so we assume the flow field to be two-dimensional, but 3 components. That is, the 3 velocity component depend only on the radial and vertical positions, and we introduce a uniform flow far upstream and let it leave the computational domain through a non-reflecting boundary condition at the bottom. So you may wonder why such a simple and inexpensive computation was not attempted before, because it's ridiculously simple and inexpensive compared, for instance, to what Stefan showed yesterday. So what is the reason? Well, actually, there are, let's say, well, maybe 2 difficulties in the problem. The first one is that, as you certainly know, there are inertial waves propagating in a rotating fluid when an obstacle is present in the fluid. And these inertial waves have the very bad idea that their group velocity, that is the velocity with which they carry energy, is parallel to the wave crest, not orthogonal to the crest, which means that actually the energy, in the case of a computation like this one, the energy tends to be accumulated within the computational domain. And if you don't do anything, actually your computation will blow up. Okay, so to avoid that, you have to use some trick, and the trick we use is so-called sponge layer techniques. That is, basically we absorb the energy on the lateral wall of the domain and on the end wall, well, on the bottom end wall. So that's the first issue, and the second issue, of course, is that you want 2 things at the same time. You want to describe properly the boundary layer around the sphere, which may be very thin if the Taylor number is large, and you also, so which means that you would like to have something which resembles spherical coordinates around the sphere, but you also want to follow the Taylor column very far from the sphere, which means that you would like to have something like cylindrical coordinates apart from the sphere. So you have to combine the 2, and well, you have 2 options, basically using either an immersed boundary technique, but well, the accuracy is, let's say, questionable in some regimes, or use an orthogonal curvilinear description, which is what we selected. Okay, so with this, we were equipped to look at the problem. So some words about the flow field in this problem. So what you see here on this slide, you see 9 configurations. So the Reynolds number is increasing from left to right, and the Taylor number is increasing from top to bottom. And in each panel, what you see on the left part is actually the angular velocity, whereas on the right part of the panel, you see the norm of the velocity. Okay? So for instance, if you consider the highest Reynolds number here and you increase the rotation rate from top to bottom, you see, well, the classical standing eddy, which shrinks little by little as the rotation is increasing. And at the end, for the largest rotation rate, there is no standing eddy at all. So the wake structure you are familiar with is totally, you have to forget it. In a rapidly rotating flow, it doesn't exist anymore. So there is no attached eddy in a rapidly rotating flow. So that's one thing. And well, if you look now at the left part, so you see the differential rotation of the flow, and you see that this differential rotation is negative ahead of the sphere, whereas it's positive downstream of the sphere, and this can be rationalized very easily because, for instance, if you write down, well, the vorticity balance for the vertical vorticity component, there is, of course, a source term coming from the Coriolis force, and this source term, you see that it involves the vertical gradient of the vertical velocity. So ahead of the sphere, of course, the velocity decreases because it has to vanish at the sphere surface. So this derivative is negative, which means that you feed the vertical vorticity with a negative source term, and this decreases the vertical vorticity. So it's natural that you get a negative angular velocity ahead of the sphere and vice versa downstream of it. Okay, so second thing, well, the inertial wave pattern. So what you see on this slide actually is a view of the pressure disturbance around the sphere, and the Rossby number is decreasing from left to right, and you see that as the Rossby number decreases, so does the wavelengths of the inertial waves. And this is what has to be expected because Taylor, when he did his experiment, could not visualize the inertial waves, but he knew they were there, and he made a theoretical prediction according to which the non-dimensional wavelengths of these waves, which, by the way, are standing waves here because we are looking actually at the steady state. So he predicted that these wavelengths should be pi times the Rossby number. And indeed, if we check this prediction, there is a very nice agreement, although the waves are highly nonlinear in this case. And another thing, you may notice that actually the wave fronts are not straight, they are bended towards the left. And because of this, actually, if you go far upstream of the sphere, you will find that the wave fronts in this graph are horizontal, which means because, well, you can write down the expression for the group velocity in this way, which means that when the wave fronts become parallel to the rotation axis, actually, there is no energy radiated far upstream of the sphere, which means that the sphere, as it rises, carries the flow energy with it within the Taylor column, okay? The wave field is not able to radiate energy far upstream of the sphere. Energy is carried with the Taylor column. Okay, so let's come to the drag. After all, it was our main motivation. So here is a plot of the compensated drag coefficient, so the drag coefficient multiplied by the Reynolds number versus the Reynolds number. So, well, on this graph, we can make quite a lot of comments. So, for instance, if we consider what happens at a given Reynolds number, you see that the larger the Taylor number is, the stronger the drag increase compared to the standard drag is, okay? So you see that the drag can be many times larger than the drag of the sphere in a non-rotating fluid. Also, of course, if you look at the bullets, which are Maxworthy data, compared to our numerical data, which are the lozenges and the stars, you see that there is a nice, or very nice agreement when the Taylor number is moderate, but as the Taylor number increases, so does the disagreement. And for the largest Taylor number, there is, well, an almost 100% disagreement between the numerical and the experimental data. Also, if we consider a given Taylor number, that is a given color in this graph, well, the lower the Reynolds number, the larger the drag increase. So you see that the drag increase is larger on the left part of the graph also. And the last thing is that you may notice that in this regime, that is in the right corner of the graph, it seems that the drag is consistently smaller, somewhat smaller than the standard drag. And actually, this is not an artifact. This is not an artifact because if you look at the pressure field around the sphere in a non-rotating fluid and compare it with what happens in a, let's say, moderately rotating fluid, you see that actually the pressure is somewhat larger in the rotating case. And the pressure being somewhat larger at the back of the sphere means that the pressure drag is smaller, and then the pressure drag being smaller, so is the total drag. But of course, you may argue, but why is the pressure a little bit increased by rotation? This also can be rationalized if you write down the balance for the azimuthal vorticity, so I don't want to spend too much time here on the reasoning, but basically, again, there is a source term which is due to the Coriolis force, and actually you can show by simple arguments that this source term is positive, which means that actually rotation tends to increase a little bit the azimuthal vorticity, and by increasing it, actually, it also produces a small positive correction to the axial velocity. And since the main axial velocity is negative because we are considering the standing eddy here, so by combining the two, actually there is a reduction of the negative velocity within the standing eddy, and by this the pressure increases, okay, and the drag decreases. So this is a very specific regime. So the regime we are mostly interested in is the one in which the flow rotates very strongly, and so here I plotted the same drag data against the Rossby number and compare it with Stewart's prediction, and you see that there is a very nice agreement between the stars and this prediction, and Maxworthy data deviate, and the smaller the Rossby number, the larger the deviation. So where does the deviation come from? So here is the highlight of the show. What we did actually is that we decided to vary the height of the cylinder, of the computational cylinder. Basically, we increased the size of the cylinder from 40 times the size of the sphere to 1,000 times. And we compare the drag we obtained with a prediction which was obtained by Tanzers and Stone in the limit of vanishing small Rossby number using a boundary integral technique. And the boundary integral technique, as you know, means that you are considering an infinite domain. So this is really the reference data, and you see how our drag data collapse little by little on this prediction when we are considering a domain which is typically 1,000 times larger than the sphere diameter. So Maxworthy's experiment were in that range. Basically, well, although his cylinder was already quite tall, actually it was only 80 times taller, if you wish, than the sphere. And in order to recover a drag in agreement with Stewart's prediction, Maxworthy would have to use a cylinder which needs to be 20 meter high. Can you imagine it? So the reason why actually this confinement effect is so severe is that actually there is a small kinematic blocking by the end walls of course. This has nothing to do with an Ekman layer in the sense that viscous effects are not involved because we are too far from the sphere, but still there is kinematic blocking because the normal velocity has to vanish on the end walls. And although this introduces only a tiny correction in the velocity field, this correction is reflected in the inner structure of the Taylor column, and it affects the drag dramatically. So last result I would like to show is this one. So again, this is the drag coefficient, which this time we compare with a semi-empirical prediction that was also proposed by Tenzer-Shenstone. And this empirical prediction is just the addition of two laws that are supposed to be valid in two separate domains. So on the one hand, there is Stewardson prediction, which is supposed to be valid for zero Rossby number and an inviscid fluid. And to this, they added, well, the Stokes drag plus a finite Taylor number correction, which was derived in the 60s by Stephen Childress. And you see that this semi-empirical prediction achieves a very good job. That is, the numerical data collapse very nicely on it, as long as the drag coefficient is, let's say, sufficiently large, which means as long as rotation effects are significant enough, and of course, as long as the container is long enough. Okay, so with this I will stop. Just let me summarize the take-home message, which is that the drag and the internal structure of the Taylor column are extremely sensitive to confinement effects, although small. And because of this, actually, there was this consistent discrepancy between experiments and theory for more than half of a century. And so what we would like to do now, of course, is especially to consider what happens in the transient stage, so before actually the flow has reached a steady state. And this, of course, implies that we would like to consider the equivalent of a history force acting on the sphere in the transient stage. And of course, let's say the Graal would be to consider the case of deforming drops and bubbles, because in that case, of course, there are two other non-dimensional parameters involved. One is the rotation bond number, which controls the deformation of the drop, and the other, of course, is the ratio of the inner and outer viscosity of the two fluids. So this is the plan for future. So with this, I will stop and will be happy to take your questions. Thank you very much.
Long live India and France friendship.